slots that are single to bytes. But then that would be equal to you just divide out pages. So that gives the number of slots. Slots for
the nice thing is it's size.
Yeah, exactly. So it returns that. Now we use directly to get, because the header page has a little bit of get slots or something. Type thing, how many slots can you put? So I'm going to it's, I guess I heard in previous classes, we did the whole project. And we give them code or too much code. There's some advantages to getting code, but the disadvantages you have to figure out what's the thing already.
The nice thing about math is too much in it all. For the most part, people do
Yeah.
whereas some characters are like, okay, this is magic. Especially if it looks like C++ or something. Arithmetic and all that stuff. So bit shifts. And so say first program is so what is it on the job? So I decided that I should check that stuff and change so that it would throw an exception if we try to add strings with and then on the reset I also check features
So let's get started. Last time, before we start, let's talk about the project. So Do you have any questions or concerns about the projects? Like, are your repository set up correctly on the so that it's showing on the status page? I noticed there are a few teams that are still not showing up. One of the team I know the reason is because your repository is still public, so we didn't add it yet. The other one is because probably you didn't provide me the link to your repository. So if you haven't done so, please check that and like set this up like before the deadline. The other thing is because we are kind of lag behind on the course lecture contents. So what's gonna be covered this lecture will be like everything you will need for your project one. So that only if you haven't started, that only leaves you about 45 days, right? So do you need some kind of extension? Yeah. So let's do a vote. How many people need a? So if we do an extension, that would be probably next Thursday. Is that fine? Let's do a vote. So do anybody want the extension until next Thursday for the project one? Okay. Yeah, that will do extension. Sorry about that because we were kind of behind the schedule. Yeah, the other thing is we released a written assignment too, but if you have a look at it, you will find out that a lot of the contents haven't been covered yet. So the way we are doing this is that we hope one thing you could do is just after a bunch of lectures, you do that just before the due date or at the time you want, because you do not need to actually hand them in. Another thing you can do is that after every lecture, look at all the problems you don't understand yet and try to solve some of them. Just do this gradually so that like it helps you to like review the course material. So that's the two ways to do it. I would say. Yeah. When's the midterm? Yeah, it's the first lecture after fall break. Okay, it's on the syllabus. Yeah. So the other reason is about midterm because we are having a midterm just after the fall break. So if we do not release the written assignment now, you will have like less time for looking at the problems because they are going to be very similar to the problems in the midterm. So we hope we can give you enough time to go over all the written assignments so that you can get familiar with the similar type of problems you will see in the midterm. Okay, so if you are still not sure how to do those problems, solve those problems, it's fine because after the lecture you should be able to. And we'll also give you the solution after the due date. So you will have enough time for that. Okay. Yeah. So that's about it. Any questions about this so far? No. Okay. Let's continue with the lecture. So. In the last lecture, we talked about buffer management, which is just like you can build a buffer pool for the pages on disks. Whenever your database, some component of your database wants to access some page or modify some page, you will first go to the buffer manager to ask for a ping on the page, right? Then the buffer manager sees if the page is already in the buffer pool and returns that. There, if it's not, it tries to find a free space for like loading that page into the buffer pool. Okay, and in the case that you do not have free space, you try to evict some of the page. Right? That's what we talked about, and we also talked about the eviction policy, the LRU, MRU, some bit of clock at the very end. Don't worry about clock. Mostly just LRU and MRU. That's fine. So. Yeah, that's about buffer management. Yeah, one thing to note, so there's a discussion on Canvas about the, let me see, is that about get page? So somebody asked me a question, I don't know if it's public. If somebody asked about the get page interface of buffer pool in SimpleDB. So, yeah, one thing about that is that if you look at the code carefully, you will find out there's no way to implement a pin count in SimpleDB. That is because if you look at there's a release page interface, but it is only called when you like unlock a page. But we haven't gone through the lock manager yet, right? So basically, the lock manager will be the very last project in this semester. So don't worry about that. And at the meantime, since you do not have a time to do not have a chance to actually release a page from like you previous get, so you don't have a chance to correctly implement pin count. So you don't have to. Just assume everybody will take care of themselves. So if some page, in the first project, we do not have to implement page eviction, so that's totally fine. You do not need a pin count. In later labs, when you need eviction policy, make sure you do not evict any dirty page. Then it's good. Okay, we will not like give you a circumstance where you have all the dirty pages and you do not have any page to evict. That's not going to happen. If that happens, just throw an exception. Okay. So does that make sense to you? Just about the project details. Okay, it's a little bit different from what we talked in a lecture. Okay. Yeah. If you do not have any question, I'll continue with this. So we also talk about disk space management. So basically, you have a raw disk, and potentially you also have a file system on top of it. But still, you might want to, you still want to like manage those pages yourself because first, when you have a heap file, you want to store them mostly sequentially, right? This way, when you scan this heap file, you will get sequential I/O, which is really fast. If you store the pages randomly on the disk, it's gonna be random I/O, and it's like about 20 times slower than sequential I/O. So that's one goal. And the other thing is, sometimes your database could span multiple actual physical files on the file system, or you want to directly use the raw disk. So that's why you still need this disk space management to manually manage all the allocated and deallocated pages on your disk, right? Instead of just relying on whatever the OS provides you. Okay, so we talk about the abstraction of database files here. So in SimpleDB, it's called DB file, which is an abstraction of records. Like each table gets a file typically, and this file will contain a bunch of records of the same schema. That's a typical setting. But if you look at, like, say, PostgreSQL, you will find out actually most of its database is actually in one file or multiple files, but they do not necessarily correspond to how many tables you have in a database. It's actually, so basically, your database file are actually mapped to different regions in those actual physical files on your file system. Or if you are using raw disks, that means you are basically mapping your database files to regions, sectors on your disks, right? So that's a little bit different from what OS provides you. But still, it's a same abstraction as you will see in the file system. So basically, a file is a collection of pages where the pages are stored in records. Okay. So to do that, you need to somehow organize the pages so that you know which pages are allocated and which are not deallocated, or which are free space, which are actually occupied by records. So we consider the simplest type of file, which is called a heap file, which is just an unordered multi-set of records. So we talk about two potential way of organizing that. One way is implement the heap file as a list where you have a full page list, which are like all fully occupied, and some of the data pages with free spaces. So you could have some records there, but it could also be completely empty. So whenever your page gets full, you move that from the bottom list to upper. And if you delete something from one of the data page in the full page list, you move that down to the page, the pages with free space, that list. Okay. So this way actually mimics what like you probably will see in FAT, the FAT file system, which is the default file system for DOS. Right?
You don't care about the order that something's added.
No, because this is an unordered file, so you don't care about the order of inserting things. Okay. Yeah. And the other way is using a directory, because directory are basically pointers to actual data pages. So because data pages are large, when you delete something or insert something, and you might need to move a lot of data, right? But and also when you need to traverse to some page, like in the previous picture, set up here, if you want to traverse to the very last page in the full page list, you must traverse the whole linked list. That's really expensive because you are basically reading a lot of pages for nothing. You just read them for that single link, then go to the next page. That's a lot of I/O to do for just a bunch of pointers. So the way you to avoid that, the way you do that is you use a directory of the pointers. So basically you have a bunch of pages that only contains those pointers to different pages. And when you want to traverse to some of the page, you basically only need to traverse the directories, okay? Because the directories are generally much smaller than the data pages, so you only need to traverse much fewer pages to get the correct point. Say you want, I'll just write it. Okay, suppose you want to traverse to this page here. You only need to follow this link and this link and get this pointer here. Okay? Then this is just one IO, and one IO here. So that's going to be just 3 IOs. But if you are going to use the linked list, how many IO do you need? You actually need to go to the first page, then follow the link, until you get to the page you want. Okay? So suppose this is 1, 2, 3. This is 12 pages, and 1, 2, 3, 4, 5 pages. So actually, you are going to pay 24 plus 5, 29 IOs instead of 3. Okay, if you use a linked list. Make sense? Okay. But still, in this way, you still could have a problem because when your file grows too large, you could still end up with a lot of directories, right? So you could, to solve that problem, you can add one additional layer of indirection. Like you have a directory of a directory. That's to say, you can have a link that actually points to one of the directory here, and some of the link in this directory will point to the actual data page. Okay. So once you add more indirections, the fewer IOs you typically, on average, you will pay for one access. But still, if you just have a linked list, if you are accessing the very first page, you only pay 1 IO. But if you are using multiple directories, the IOs you are going to pay is actually the number of the number of level of indirections you have. Okay, but that's just a trade-off. Typically, this is better because on average, it provides a much smaller, and it is a constant number of IOs for each page access. Okay. And this also mimics like something called ext4 or Unix file system, something like that. Okay, they also use the same techniques. Okay. So yeah, so we talked about heap files. There's another important kind of files in databases which are called indexes. So basically, the heap file are a bunch of like unsorted data they are on order. They do not have a specific order. So when you try to like find some specific item, like find the student record with student ID 105, you have to scan the whole file to find that. Okay? If that particular record happens to be in the first page, you're very lucky. You just scan the first page and you find that record. But if it's in the last, it's the worst case, right? You have to traverse the whole file until you reach that record and return that record. Okay? So a heap file, actually, so in the worst case, you need to scan the whole file for just find one particular record satisfying some condition. On average, it's half the size. Okay? But sometimes we do frequently need to access some record according to some particular predicates or conditions. Like we want to find a student with GPA greater than 3, or all the students in the CS department, or just find a student with a specific student ID. Okay, so that's where the indexes are like useful. Basically, an index is a file structure that enables us to quickly find a set or multi-set of records that satisfy certain conditions. So the type of conditions, depending on different type of conditions, like if you have an equality condition, you can build a hash index, you can build a B-tree index. If you have a range, then hash index won't work, right? So you have different kinds of indexes which apply to different type of conditions. Don't worry about B-tree or hash, we will talk about that later. But just that to handle different type of search with different type of conditions, you need to have different kind of indexes. Okay? So we will talk about in detail the hash index and B-tree index later. Okay, so that's an overview of what we have as files, like key file and index file. And the next thing to consider is that how do we actually store a record? So we only talk about we are going to store records in those pages, but how do we store them? So each record must have a format, right? So as we talk about, so each record will have a schema. Basically, in one database file, all the records will have the same schema, but it will have some kind of schema. So depending on whether you have variable length fields or not, you can end up with different record formats. For example, here, so if all your fields are fixed length, that means all your fields only have a constant length. Like you have an int field, you only have all int field. They are all 4 bytes in length. Okay. Then the way you organize that is you just store them consecutively. So basically, suppose the base address is B. So this is the base address B, and suppose this is int. This is 4 bytes, right? So you just store it until B plus 4. So basically, it will occupy B to B plus 3. Is 3 bytes. Okay. Then the next one would be, so suppose this is actually write L1. Suppose its length is L1. Okay. L1. Then you just store the next field consecutively. So suppose this is a double, which is 8 bytes. Then this line here would be which one? B plus L1 plus L2. And the double field will occupy the bytes from B plus L1 to B plus L1 plus L2 minus 1. Okay, and so on. So since you have a schema, remember schema is something that's fixed. So it's not going to change. Typically, it's not going to change in your table. So in that case, if you have a set of fixed length fields, you can predetermine what offset they are compared to the base address. Okay, so suppose your table is just a bunch of int, double, int, and int, right? You know this one will be at b plus 0. This one will be at b plus 4. This one will be b plus 12 and b plus 16. And the total length of this record will be 20. This is the total length. Okay. So that's way how you like calculate the offset and actually store this record in your pages. So you don't actually need to remember this 20 here. That is because since you have a fixed schema, this can be pre-computed, right? Because everything is fixed. You know this beforehand. You do not actually need to calculate that. So in reality, how you do that is basically say this is, you have a pointer b, which is just a normal bytes, something like a character pointer here, right? And this, say you read that from some kind of page. So let's say just get rec and some kind of rec ID. And when you want to access, say, field 2, you just do f2 equal to, so you cast that to its type, and do b plus 4 and do a dereference, and you get the value. Okay, this is how you actually get the value. Okay, make sense? Yep. So, any questions about this approach here? Like how to read this thing, how to write this thing, and you know this is basically a bunch of bytes, so you can store it in a byte array. And when you need to write it to some kind of page, you do a man copy. Okay. So the next thing about here is, what if you have variable length records? Okay. So suppose your schema is like you have int var character 10, and say it's just double, okay, just for like 4 fields. You know, this one is variable length because it is a var character instead of character. That means this the length of this string could be smaller than 10, but you will not exceed 10. So how do you store that? So one way is to, the simplest way is just use the maximum length. So basically just waste a bunch of bytes. Use the same format as the fixed length record, but that way you are going to potentially waste a lot of bytes, because like here this is only 10, what if it's 1,000, right? So if, or like most likely if most values in this field are only 10 bytes in length, but maybe 1 or 2 of them are near 1,000 bytes in length, then you're essentially paying, like you're wasting 990 bytes for most of the records. Okay, so that's not going to work in a general database. So the way to do that is you can either do this, use a special character to specify the end of each field, like the dollar here. So basically, this dollar will be some kind of bytes that's not going to appear in your fields. So maybe just like that. So for var character, it could be some kind of invalid combination. So you know Unicode, right? In Unicode, no, actually not. So suppose like that. So suppose you have ASCII code, which is 1 byte, right? Which is 0 to 255. All right. So in C, actually, if you are writing in C programming language, the end of a string will be a 0 value, right? So basically, if you write character ABC, that's going to be an array of a bunch of bytes. The first byte would be 97, 98, 99, and the last one would be a 0. So if you do not allow a null character in your var character field, then you could use this 0 as a end of this field, this indicator for this end of field. Okay? But in reality, I don't think that's something you could do, because for var character, actually you do allow a null character here. So in reality, I don't think you could find something meaningful for this separator. But if you can find, then this is an option. Okay. The other possible way is to remember what's the offset. Okay. So first you would have a slot array for the fields. So this is called a slot array. Well, we will also mention a slot array in the page format, in addition to this record format, but don't get confused about that, because they are all called slot arrays. So basically, this slot array will be a bunch of offsets. The first one will be pointing to the start of the first field. This is the first one. And the second one will be pointing to the start of the second field. Because every field are stored consecutively, so the beginning of the second field will be the end of the first field. So in that way, you can determine where does the first field start and end. And also for the second field, where does it start and end. So in general, for field I, the start of it will be the slot I, and the end of it will be slot I plus 1. That's something like this. So as you can see here, actually you do not have a pointer to the very end of this record. Why is that? So don't you still need a pointer for that, so that you can find out how long the last field is? What do you think? Any suggestions? Yeah. So if this is, I would say, if this is just record itself, it's not correct. But in reality, because as we will just mention later, in a page, because these records are actually stored in pages. So in a page, you will you will save the length of the records there. So once you get the length of the records, so suppose the total length of this is called total length, okay? This. Then basically this is just total length minus the size of the slot array. Okay? I mean the last bit of this. This is from the first one, right? So the total length minus the size of the slot array is the offset of this point from this point. Okay? And that would be that.
So the length includes
Yes, typically total length will include the slot array. It will include everything in the record. So maybe it depends on how you calculate this. If you want the offset from this point, then just use total length. If you want the offset from this point, just minus the length of the slot array. Okay? But this total length is typically not recorded in the records themselves, for the reason we will talk about later. But it will be stored somewhere else, like in the page. Okay? So that's why we do not need a pointer here. Yeah. Okay. But yeah, that's about it. But of course, you can also store this right here. Yeah. It's another alternative that you store total length here. Some database also do that, but then you do not store that in the page. Okay. Yeah.
So what's stored in those slots?
What's is stored in the slots? So basically, these are offsets. So you can think of them as some kind of pointer. So suppose this is 0, 4, 8, 12, 16, okay? So basically you will store 16 here. Then when you get the base address of this record, you just do b plus 16, then you get the start of the first field. And the second one, suppose this is 20, then you store 20 here. You do b plus 20, then you get the start of the second field. Okay, that is to make sense?
So it's the number of bytes? Or the number of
Yes,
bits?
number of bytes. Offsets are basically number of bytes between 1 point to another.
Is it bytes or bits?
Bytes. Bytes.
Bytes.
Yeah, typically bytes, because your memory is byte addressable, it's not bit addressable.
Yes.
So bytes are easier to use.
So it's the number of bytes.
Right.
Now, these slots can only, they have to be a fixed length themselves. Right?
Yes. Because why is that? Actually, you only need a fixed length because a page has a fixed length. So, like typically, like a file system page is 4 kilobytes. A database page may be bigger, like 8 kilobytes. Then so how many bytes, how many bits do you need to address like 8 kilobytes of memory? That's only 13 bits. So it will fit in a 2 bytes integer. So typically we will just use short int here. Okay, that's enough. But for the base address, that's going to be a standard pointer, but you will add that short integer to that base pointer. And so, yeah, we haven't talked about actually how to store the nulls, right? The second thing also provides a way to actually store null. Suppose you have a null value here. Instead of having a value pointer, you can just write a -1 here. Suppose this is null. If it's null, write like say a special value like -1. Then it indicates that field doesn't exist. So basically what it says, the field doesn't have a value, it's a null value. Okay. So that's the way you encode null in the second option. But in the first option, you do not actually have a way to encode null. Because suppose you just do for the third field, it's a bar chart, right? A bar character, right? If you do not fill anything here, so nothing here, nothing here. So what you are gonna see is the first dollar and the second dollar. So nothing in between. So how do you distinguish this between a null and an empty string? How do you distinguish between them? Okay. So if you use the first format, it's not distinguishable. Okay. Yeah, because if you do not have anything in between, you do not know if it's a null or an empty string. So basically, in the first format, you do not actually you can only use this on something that's not nullable. So that means you cannot store null then. Okay.
Why can't you just, in the first format, include the length of each of the fields? Then you can store null.
Yes, but that's essentially to the second way. That's the slot array, right? Yeah. Using a slot array, you have a chance to actually encode those nulls. Okay. Yeah. But in some systems, what's this? The CD. So basically, in some systems, I also have seen some of them who have a bit array at the very beginning to indicate whether some fields are null. Basically, you still have the standard like offsets here, or you just use this. Then you store a bunch of 0, 0, 0, 1. Okay, say that's that. Those are a bunch of bits. Remember, these are bits. So these are bits. Then these are basically saying the first field is not null. The first field is not null. I just point to you. So if you store a bit array like this, this is saying the first field is not null, the second is not null, third is also not null, but the fourth field is null. Okay, that's another way to do that. So basically, you can use the first alternative or the second alternative without actually especially handling that null value in the slot array or somewhere else. You can just append the bit array to the beginning of this or the end or whatever offset you want of these records and to indicate whether some of the fields are not. That's also an alternative. Yeah.
I'm having trouble with how negative one represent null, isn't it? That's some offsets.
No, it's not gonna mess up your offsets. So let's do a fresh page. Okay. Yeah. Suppose you have a slot array. Suppose you have a slot array like this. It's saying same 16, 20 minus 1, and it would be 20. Okay? So basically, oh no, sorry, 24. Yeah. Suppose our schema is still int bar character and int. Okay? So what you're gonna have is this is an integer. This is an integer. This will be nothing. And so this is 16, 20, 24, and 8. So whenever you are trying to find some offset like this, so you try to find the second field, you're going to find this offset here, right, 20. And this is the start of F2. Okay? 1, 2, 3, F2. And if you are trying to find the end of F2, you can do it in two ways. Because this is a fixed length field, you can simply just add 4 to that. Or you can do it in a standard way, which is find the next slot here, and you find the -1. So that's going to be indicating this field is actually a null, right? So you do not know what's the end, but what can you do then? You just go to the next one, right? Because this is null, it's not going to occupy any space. So next offset will be in the next non-null. So you just go to the next until you find something that's not -1. Then that will be the end of F2. Okay? So that will be the end of F2. So does that answer your question? See what's going on? So
So you're not actually adding.
no, what do you mean by adding a negative one? Negative one is stored here.
Here. So 16 is an offset, and you added 20 to get the next delivery.
Right. It's just this is just a special value. Whatever you add based on is something here. Okay, so the next one, the next non-null field will be based on this field. Okay, here. Yeah. So so this is F2's start. Okay. This is supposed to be F3's, but it's not. So it's not occupying any space. Yeah. So the actual non-null will be here, F4. So F4 is based on the 20. You add 4 to that.
You want to store like 3 or just put it in at 28?
What do you mean?
You want the store value for F3, put it at 28?
No. So let me see. No. When you want to say you want to set this null value to something else, to some non-null value, you reorganize the entire record in a way so that it's inserted here. So it's going to be a completely different record.
So you have to reorder it.
Yeah, you just reorder everything in order. That's That's what's going to happen. Yeah. So it might sound very expensive to you, but in reality it's not, because disks are really, really slow. You are doing this basically in memory, so you are just doing a bunch of memory copy, which is happening all the time in your database system. So once you are done with a bunch of memory copies, you basically reorganize the records and pages. You write everything back to the disk. Yes, a record is always going to be continuous in memory because it's in a page. I'll just come to that. But basically, what you're going to find is that a record is basically a contiguous array of bytes. Then each record is stored in a page. A page is a contiguous chunk of a huge chunk of bytes. Then it will be stored somewhere in that page. And when you read this into memory, it will be a contiguous space in your memory. Yeah. So for that, we talked about records, but still we need to put those records into the pages, right? Because files consists of pages. So what you can do is, if you only have fixed length records, remember that for fixed length records we know the length beforehand. So what you can do is that you can have a slot array here. You can have two things here, not a slot array. Because if you decide everything should be packed. Packed means your records are going to be stored contiguously. So you cannot have holes inside those records. Like you store one here, and next will be 2 and 3 and 4 and up to n. And you just store how many records you have of them. So then you know the slot 1 will be at 0 offset. And suppose the total length would be, suppose it's 28, okay? Then the second one will be at offset 28 of the page. And the next one will be 56, okay, and so on. The nth will be at 28 times n minus 1. Okay? That's how you do this in the packed array. So if you are going to insert something in the packed array, what you're going to do is that you append the next one to the free space here. So you look at the n here, and you store the next one, store the record, plus 1 to slot, and plus 1. That's at offset 28 times n. Okay? And you update this to n plus 1. That's for insertion. Okay? If you do a deletion, if you delete something at the very back, like at the very end of the slots, that's fine. You just deduct 1 from the number of records here, okay? Then it's good. But what if you delete something that's in between? Like, so suppose, let's go back. Suppose you are gonna delete this one here, slot I here, the record in slot I. What's gonna happen? You're going to have a hole here, right? So basically, this slot will be empty. It will store nothing. Then you still need to update this record number of records to n. But then your offsets are messed up. Okay, your anything that's before I, that's fine. They still work fine. But anything that's after I, you have to add 28 to that. But that's not good, right? So that basically. You do not have a way to store that in this form. So basically what you're going to do is that if you delete something in between, you move everything up. So you do a memory copy to copy everything that's below it to this offset. Okay. Then you don't have a hole in between and your offset still works. Okay. That's how you do that. Yeah. The other way is to use an unpacked array, because this way you constantly need to reorganize the pages if you delete something or only when you delete something. Okay? So if you do not want to reorganize the page, you can just create a bitmap here. Okay? So this is a bitmap. So a bitmap is basically a bunch of bits. So suppose you have m slots, which is the maximum number of these fixed length records you can have in this page. So then, if you have m records, how many bytes do you need for this bit array? That's m divided by 8, right? And take a C that. So that's the number of bytes you need because each byte has 8 bits, and each one can encode whether a slot has a record or not. Then the next thing you do is that whenever you insert something into this page, you first find the free space, say this one, say this is slot 3 and it's free. Then you update this 0 to 1 and actually insert that record here. So do insert record. Okay. Then you just successfully inserted this record. Okay. And when you delete something, what you're gonna do is basically mark this. Say you are deleting slot n, delete the record from slot n. You want to delete record. What you're gonna do is basically update the say this is the 8 bits. You just update that and you will find. Okay. That basically the 0 here just indicates the n slot is empty from now on, and the record there is deleted. You do not actually need to override the data here. You just update the bit rate, and that's fine. Okay, make sense? So just a simple question. So suppose my page has 8 kilobytes. This is an 8 kilobyte page. How do you compute how many? What's the m value? How many records can you store in the page? Yeah, anybody want to try it?
Take your page. If you do it very similar to the simple DB, take your page times it by your bits to get the number of bits in a page. Divide that by however big your record is. Then you add one record in bits. Add the one additional for your header.
Yes,
And
that's
then
right.
do the division. You get the number of.
Yes, that's right. Typically, we will still have a header here, right? But just for simplicity, we just ignore the header for now. If that's the case, basically it's going to be 8 kilobytes divided by, divide the equation here. So basically, 8 kilobytes will be m times the length here, that's 28, plus m divided by 8 and the city. Okay? So just do that and solve this equation, you get the m. Okay? That's how you do that. So actually, this should be a unique. It should be this way. Because like when you have something at the very end of this this page, you will have some like fragments over there because there's some space that's left, but they do not fit one record. Okay. So that's why you want this inequality here and solve for the maximum m you can get. Okay. That's how you get that. So we talk about the fixed length. The other thing to think about is that what if you have variable length records? So just in case, yeah.
Why is great?
Sorry.
Why is this great?
Oh, why is that? Yeah, so this can happen like, sorry, I write it here. So suppose your page can fit a bunch of records, and you have a bit array here, right? But at the very end, you have a bunch of space that's still free space, but doesn't fit record. So your record doesn't fit in this very small chunk of bytes. Okay, what happens? So if you list the equality here, basically you are gonna get not a whole number for n. Okay, so that's why you want to list this inequality and solve for the maximum n you can get.
And then it should be the same. In fact, also we are basically wasting that space.
Yes, basically you are wasting that space. But wasting space is actually good for database because just in case. So sometimes we deliberately waste some space there because when we have an insertion, say we just want to insert here, then we have some space there. So how do you identify? So for each record, you should have an identifier for that. That's called a record ID. So how do you specify that? So basically, it's gonna be a page ID and a slot number. Okay, so it's a combination of page ID and slot number. So when you want to identify a record, you just say what page it is in and what slot it is in. But there's an issue actually with the pack approach. What is that? So yeah, so whenever you are deleting something and you reorganize the page, the record ID changes. Okay, so suppose you have a pointer from somewhere else into this record, then it's an invalid pointer, it could be, or it's an incorrect pointer. So the first alternative is actually really expensive to implement because in reality, because you have indexes, you have a bunch of other data structures you might have, like ongoing transaction that has cached some kind of record IDs. If you just reorganize the page, then you have a wrong pointer or even dangling pointer. That's really bad. But with the second approach, it's not gonna change a lot because what you do when you delete something, you do not change others' slot number. You just mark something as deleted. Then everything else won't change. Okay? So suppose you say this is page 1 and slot 1 here. Okay? And if you delete this one here, this one is still 1, 1. Okay? Because everything you do is basically mark this nth bit as 0 and nothing else, nothing changes. So in reality, I would say the first one is not very practical unless you are sure there's no pointers or you are able to update all the pointers when you do this overall. For the second alternative, it makes much more sense because you do not need to handle a change pointer, changing the pointer once you do something. Yeah.
So you do something,
Yep.
and you go to add something like maybe use put it in this spot.
Oh, that's a separate issue actually. So when you delete something, remember in the database we have to guarantee integrity, right? Integrity constraints. So if you have pointer, say it's a foreign key reference, okay? Then when you delete this, you notice there's a foreign key reference. Then you cannot, or if you're cascading cascading deletion, or just a for this deletion. So that is actually not guaranteed by the page format. Instead, it's guaranteed by up-level logic to guarantee those integrity constraints. Yeah, but yes, that's an issue to handle. Like in reality, you do need to handle that in up-level logics. Okay. And so the next thing to think about is that what if you have variable length records? So if you have variable length records, of course the fixed length record page won't work because basically your records are going to have different lengths. What do you define what's a slot? If it is the largest possible length of your record, it's going to waste a lot of space, just as we discussed in the variable length record format. Right? If you just define the maximum size it will have, then basically you are wasting a lot of space in your slots. So if you want to store things more compactly, basically you need to have some sort of directory of these slots. So that's a slot array. It's the same idea as the variable length, the second alternative of the variable length record. Okay. So basically, you are going to have this slot directory or slot array here, this one, or you can call it like the slot array. It's easier. So what you're going to do is that you can choose to have a pointer to the start of a free space. Yeah. So at the first point, you will have something, a pointer that points to the free space. Suppose everything is packed, still packed, okay? So basically you have a bunch of records at the very beginning of the page, and you have a pointer point to the remaining free space. Then if you say there's any slots, that means currently you have ever allocated any slots, and this array actually grows backwards. So if this is, so suppose this is B plus 8,192, that's 8 kilobytes. And this pointer will be at B, suppose this is called B prime, okay? This will be B prime minus 1. And this one, the number of slots will be stored at B prime minus, not 1, 4. Suppose this point is 4. Everything is 4 bytes here. This is B prime minus 4, this is B prime minus 8. Okay? And this is the start of your slot array. And it's, so the ith entry in there will be at offset B prime minus 8 minus I times 4. Suppose everything is 4 bytes. Okay? Then what you storing there is basically two things. So an offset and the length of the record. Okay. Sorry, it's not showing. So basically you are storing. So suppose the length of this first record here is 28 bytes. Then you are going to store its offset, which is 24, and 28 here. Okay, that's going to indicate what's the beginning of that and what is the length of the record. Remember, in the variable length record, we do need the record length, the total length. It's actually stored here. Okay. Then for the next one, for the next slot, we're going to have, like, say, 16, and suppose this is 8 bytes. Sorry, let's do 4 bytes. Then you're going to store 16 and 4. Okay, and so on. So whenever you delete something, you can mark that as minus 1. So suppose you are going to delete this one. Basically, what you're going to do is that you mark this as minus 1, minus 1. Then that indicates this slot is actually empty. It doesn't point to anything. Okay? And when you insert something, you first search through the slot array to find the empty slot. Suppose this is 1. Then you find some kind of free space using this pointer, the pointer to the start of free space. Then you try to put the record up there, and so suppose this is 0, and your record length is, sorry. So suppose this is your free space, and this is 4096. Okay, and you store a new record here with a length of 30. Okay, then you basically change this to 4096 and 30. Okay, using that old slot. What if you do not have any empty slots in the slot array? You just grow the slot array further. You have n plus 1 slots. Modify this to n plus 1. And store the next one here. So suppose this is 4126, and this is 24. Okay, you just add a new slot here and change this number of slots to n plus 1, and remember it's 4126. Make sense?
This allocation will be always in continuous.
Yes, that's a point of here. So I didn't mention that. So when you delete something, you have two choices, basically. You can either choose to pack things, which is exactly what this format requires. Because you have this pointer to the start of free space. So whenever you delete something, whenever you have a hole inside, you need to compact it. Okay? Yeah, you just move everything and update their offsets here. But remember, that's actually good. That's actually okay for the problem of like changing record ID, because here the record ID would be page number, page ID, and the slot ID. Okay. So whenever you move the records inside the page, this slot ID doesn't change. The only thing that changes is the offset inside that slot. Okay. So this way you can actually compact things. Make sense? Yes. Basically, you are moving things over and over again. That's really expensive, right? Yeah. This is just sorry. I'll just come to you in a minute. Yeah. Let me finish this. So this is actually two choices. Either you can have a pointer to the start of free space, or you can try to just scatter things around. And when you try to find some free space, you scan through the slot array and try to find a hole that's big enough for a record. And when your page is too fragmented, that's to say all your holes are too small for the next record, or basically they are too small, then you do a compaction. Yeah. Yes?
So why putting the slot array in instead of beginning as before?
Yeah, that's a good point. So why do you put it in the end? Can we just put it at the beginning? Can we? What do you think? Yeah. So what if this happens? So suppose let me create a new page. Sorry. What if you have a huge page? What if you have a page here and you have a slot array here? So say this is n and 1, 2, n, right? And you start putting records here. These are rec 1, rec 2, and so on. Okay. What if all of your slots are occupied and you want to insert one additional record? What happens? Where do you grow that slot array? If you do this, you do n plus 1, but you do not have a space after this n slot for that n plus 1 slot.
So you lose your space there.
Yeah, so how many space do you want to keep? That's a question too. That's a decision to make, right? That defeats the very purpose of this slot array. Like this slot array is supposed to make like every insertion and deletion as cheap as possible. So you do not want to do a lot of rearrangement. So whenever you want to insert something, if you are just inserting things, you shouldn't be doing any. If you are doing this way and you are so the number of records are inserted into this page are larger than what you anticipated, you're going to have to reorganize things, right? But what if you put it at the very end, like the previous page? So basically, your records are going to start from the very beginning of the page and grow grow forwards, while your slot array will be starting from the end and grow backwards. Now, it will just like when your page gets full, they will just meet in the very in the middle of this page. So when you are inserting contiguously inserting records, you are not gonna have any reorganization for this page, because your records goes forwards and your slot array goes backwards, and they will meet somewhere in the middle. But if you are put this slot array at the very beginning, you might have a chance to have to reorganize this page if something, if your number of records is larger than what you think it will be.
Okay, so another question then, it's here that you have huge amounts of space between records.
No, actually not. Actually not. So here everything is packed. These are packed actually. These are free spaces. The white stuff are actually filled with other records. They are are stored contiguously. So it's just not showing here.
What's the black?
Yeah, black just indicates some of these records. So basically, this is just an example. Okay. So so everything else in the white background will still be some part of the records. So you will have other pointers from the slot array pointing to that. So basically, in this format, everything is packed at the very beginning of this page, and at the end of this page, except for the slot array, they are free spaces. Does that make sense? So whenever you insert something, you put that to here and update this pointer. If you delete something in the middle, you move everything to fill that hole in the middle and update this and all the offsets here. But remember, because you are only updating the offsets, the slot ID doesn't change. So your record ID will change. So it's different, totally different from the pack format for fixed length records. It works more like the second alternative of the fixed length.
Okay, what's the difference between the second and the third?
Oh, that's the second one. You mean the one from the previous page?
Yeah.
Yeah, that's for fixed length records. So everything there are of the same length, but everything here can have totally different lengths. Okay, make sense?
So there's not slots here. You just have records of variable length, and you're packing records.
Yes. Basically, you are packing them, but you still need to remember their offsets and lengths. They are actually stored in those slots. That's what this slot array is.
What if they change length?
What if they change length? Basically, you do a reorg of everything.
How do you define that?
No, that's not going to happen in your database because you are packing, right? So when you are like, if you are changing something that have a different length, what you're going to do is do a deletion first and do an insert. That's how they do that actually. Yeah, so this might sound silly to you, but in reality, this is actually not necessarily a bad way to do it, because this is just remember, these are all in memory. So basically, you are operating in memory, and memory operations are much more faster than any disk operation. Yeah, so because your database still needs to access the disk when you change something, so that disk write time will mask everything out. Basically, even if you do a whole bunch of memory copies, it's still much cheaper than the time you spend on writing the whole page out.
So if you add one field to the very first record, the entire page has to be reorganized.
Right. That's right. That's right. Yeah, that's what's gonna happen. Yeah. When you delete, so when you delete a record in this format, you need to first mark this slot array as -1, Then this is a hole, right? You move everything that's behind it to fill that hole. And yeah, you will never have a hole in this format. So basically, then you will just update this pointer to start of free space to somewhere like newly free. Okay. So basically, all your occupied space will be at the beginning, then followed by free spaces, then followed by the slot. Yeah, there will be -1 in the slot because you do not want to change the record IDs. Yeah, as I said, the other choice is to not have this pointer to start of free space. Then you can just like do not pack things when you have a hole. Well, remember in that case, you could end up with the situation you have enough space for the next record, but none of the hole will fit that record. Then you still need to do a reorg. Right? That's just like, do you do a eagerly reorganization of the page, or do you lazily do that reorganization of the page? It's just a strategy to choose in like implementing this variabilized page format. Okay.
These are all the records from the same table.
Yes, they are all the records from the same table. So basically, a file will consist of pages. Pages will, no, I mean, there will be one file for each table. So basically, all the pages will for this to the same table. So yeah, let's start. Yeah. So we're done with the page format, record format. So yeah, in simple DB, let me think about it. How to do that? So in simple DB, actually, I think it's everything is fixed length. So I think it will be something like this. No, sorry. It will be something like the second alternative. Okay, in simple DB. But there will be an additional page header. A page header is basically some metadata about this page and will be fixed length, like something like what's the version of that, or whether this page, what this page belongs to, something like that. Okay, so that will be a fixed length part at the very beginning. So when you compute the m here, remember to subtract that size of header page from the left hand side. Okay. And I think it will be something similar to the right-hand side. If not, it will be a combination of the right-hand side and this format. But everything is fixed length, so you do not need to actually store a record length there. Okay. And yeah, so regarding the record format, I don't think you actually need to understand the record format for SimpleDB because the tuple class actually just store everything as a field array. Each field is just a Java object. Yes, so there will be a field class, and we'll have two subclasses called int field and string field. They are both fixed length, but basically in your tuple class, you will have an array of fields. Then these fields will point to those different fields. But this is just in-memory format. So when it's on disk or it's in page, when it's constructed from page, in the page is still stored in the format as we described for the page format. But when you are operating on these tuples, it will be converted to this in-memory format as pointers to fields. Okay. So it's a little bit different. Yeah. So yeah, we still have 5 minutes. About 10 minutes. Let's finish this. We can finish all the things here for disk space management. Once we finish that, next lecture we will talk about different access methods. Okay. So the next thing to talk about is called system catalog. So basically, you have a bunch of files, records, tables, databases in a database. Yeah, databases are also objects in the database because you can have different databases in the database system. Okay? So you need to have some way to tell, what's the schema of them, where are they stored, and what's the format for them. Because in a database, typically when you are dealing with a database with a long history, the record format could change over time. Okay. So basically what they do is basically they mark the different record format with a version number, and you could end up with different record formats even in one single database system because of this upgrade of database. Say you upgrade your SQL Server from 2000 to 2016, something could change. Okay, so that's why they might need a version indicator for that for the record format. So those are all called metadata about the database records, tables, and everything in the database. So where are they stored? They are basically stored something called a catalog. Okay. So this system catalog themselves are actually stored as relations or tables. So they are no different from an ordinary table, except that they always exist in your system, and they are pre-populated when you initialize a database instance. Okay. So here's an example. So suppose you have this attribute cat, which is just about every attributes in your database system. So that's basically you put, so suppose you have a bunch of schemas for different tables. You need to have somewhere to record what's the columns in those tables and what's the type of them. So basically you put everything into this one table. You can have an attribute name and what's the relation it's in, and what's the type of the field and what's the position of that. Is it the first field or the second, right? Something like that. So this is just a very simple example, very simplistic, and in reality, the things are much more messier, and a lot of the fields in this catalog will make no sense to you because they're just internal stuff. But these things actually you will see some correspondence in real life. Okay. So let's take PostgreSQL as an example. Basically, Postgres has I would say that's a schema called PG catalog. I don't remember if it is a namespace or schema or database. So it will have something called a PG catalog, which contains all the views and tables for those system catalogs. So, just as an example, so if you have a table, there will be actually a table called PG class. It writes this way. We'll call it PG class. This will contain all the information of all your tables. Like you will have the table name, the owner of the table, and the object ID of that, and something else. Okay, and you can actually query that. So if you want to know the schema of the system catalog, you can use these commands. Use the same /dt for those system catalogs. And this information schema is actually something that's defined in the standard. So you will have this. This is actually a view. You will have this view on almost all standard forming systems. Like you have this in MySQL, in PostgreSQL, in SQL Server, in Oracle. You will all have this particular view, but it does not necessarily contain all the information that this particular database system will record. Like each database system have different internal designs, so it will have additional information. So that will be in their customized catalogs. For example, for Postgres, that would be something starts with PG on the screen, like something like PG class. That's for the information metadata about your tables. Okay. Then suppose you want to find out what's all the attributes in the table for payment. Then you can do a join on PG attribute, which is something similar to what we see as that ATTR cat, okay, attribute catalog. That's something similar to this, but it will contain more columns. And so it does not actually have a relation name. Instead, it's joining that with the actual table using an object ID, OID. So basically, everything in Postgres will have a unique object ID. Actually, not unique because columns, each column are assigned an OID, but not each value of your tables. So, but each table will have a different OID. So you can join that attribute relation. This is actually attribute. This is actually attribute relation ID. And you can do a equi-join on this PG attribute and the PG class on this ID, and it should match some of the OID in the PG class. And in PG class, you do have a relation name, and you specify that as payment. So basically, this query gives you all the columns in the payment. Okay. So because they are just to prove the point that these catalogs are just normal tables, ordinary tables in a database. So you can actually issue queries against them. Actually, in database systems, whenever you issue a query and you need to find the metadata, it does no different, not something different from traditional queries. You just issue a standard query to the system to get those information from those columns, tables. Okay, this is just an example to show you what a catalog is. It's basically about metadata. So metadata are typically persisted on the disk, but in SimpleDB, it's only in memory. So don't worry about its format and how it's related to the relations. So don't worry about that. Okay. So just last bit. So in summary, we talked about all the memory hierarchy and buffer management and disk space management. Okay. Yeah, sorry that. So that's so this is
the back.
just this part is just the first basic.